read through this definition of what point of diminishing returns is. And then I'm going to put up a poll of the word that we have learned in this chapter that would fill in this space. So I'll give you a few minutes to go through that, and then we'll talk about it together. Okay, so before I put up the poll, let's read through this. So a company decides to increase spending on advertising. At first, sales will increase at an increasing rate, then increase at a decreasing rate. So sales are continuing to increase. If we're putting more money into advertising, sales are increasing this whole time. But we're saying at first they're increasing at an increasing rate, and then they're increasing at a decreasing rate. So the dollar amount X, at which the rate of change of sales goes from increasing to decreasing, is called the point of diminishing returns. Mathematically, this is the X value of the what of the sales function. So I'm going to put up a poll, and then we can talk about it and possibly do the poll again if we want to. Okay, so there are 4 words that we've used in this chapter so far. Which one do you think goes in this blank? Okay, about 15 more seconds on that poll. All right, I'm going to end polling now. Okay, so the majority chose the right answer. So before I reveal what that was, let's talk about this. So this company is going to spend on advertising. And as they spend on advertising, sales are going up. So this function is going to be increasing on the whole interval that we're looking at. It says at first, sales will increase at an increasing rate. So what that's saying is that the increase is getting faster and faster and faster. So the more money we spend on advertising, the sales are actually getting more and more and more. So it's increasing at an increasing rate. So the slope is positive this whole time, but it's getting steeper and steeper and steeper. But then eventually, the sales are going to increase at a decreasing rate. So sales are still going up, but it's starting to slow down. So as we put in more money for advertising, the return we get per dollar is diminishing. We're getting less return per dollar as we spend more on advertising. So this point, if we were not talking about any context, and this was just a graph that we were looking at, that would be the inflection point. So that was the correct answer here. The difference is that an inflection point, we always say the X and the Y unless we're told just to write the X. But here, the point of diminishing returns is specifically just that X value. So this is the point of diminishing returns. So before the point of the diminishing returns, the more money we spend on ads, the more each dollar is doing. Sales are going up more and more the more money we put in. But then after that point of diminishing returns, sales are still increasing, but each dollar is doing a little bit less because it's starting to slow down. And the other thing we can notice about this is this starting blue part, is that concave up or concave down?
Up.
Up, exactly. So the curve is going up, and if we put little eyes above it, it would make a smiley face. Whereas this one, the other one, is concave down. So the curve, the opening is down, and if we put little eyes here, now it's a frowny face. So these point of diminishing returns problems, all of the parts that we're going to be doing will be nothing new because you've already done work with finding inflection points and concavity, but the way the problems are worded will be different. So you have to do a little bit of thinking to figure out what is being asked here. So here is our first point of diminishing returns example. Or it's actually our only one. Okay, so we have a store is selling 200 TVs monthly. If the store invests X thousand dollars in an advertising campaign, the ad company estimates that monthly sales will be given by this function. So N is the sales and the TV sales, and X is the thousands of dollars that are being put into advertising. And so we have two parts. So focusing on part A, the question is, when is the rate of change of sales increasing and when is it decreasing? So if the rate of change is increasing, we have a way that we normally say that in math in this section in chapter 4, and the rate of change decreasing, we have another way of saying that. What words do we use to describe the shape of a graph where the rate of change is increasing or the rate of change is decreasing?
Critical number?
Not quite. The critical number would be when the rate of change is 0.
Oh, okay.
Or undefined.
Rate of change increasing is concave up.
Yes, exactly. Rate of change increasing would be concave up. Oops, got the U. So that is when, in this case, our rate of change will be positive. So I'll just use that. So if we have a positive rate of change, but it's getting steeper and steeper and steeper, that slope is increasing here. So we have something that's concave up. The rate of change decreasing would be concave down. So now rate of change is still going to be increasing for, or still going to be positive for this problem, but it is slowing down. So now it's concave down. So really what this part A is asking is, when is this graph concave up and concave down? It's just asking it in a way that's specific to this application of a problem, because asking when sales are concave up and concave down is maybe not as clear. So we're looking at when the rate of change of sales is increasing and when it's decreasing. So if we want to find where this, where sales are, rate of change of sales are increasing and decreasing, that means we need to find where this function is concave up and concave down. So this is our function. What is the first thing we need to do to start to figure out? Yes, the derivative. So n prime is 12x squared minus 4 times 0.25 is just 1, so that'll be minus x cubed. Yeah, that's right. Okay. This polynomial is out of order, so that threw me off. So we have our first derivative. What do we do next?
Equal to 0.
Not quite.
Take the second derivative.
Second derivative.
Second derivative, exactly. Anytime we're talking about concavity, we need that second derivative. So 24x minus 3x squared. So now we can set this equal to 0 and solve.
Pull a 3 out. A 3x, actually.
3x, yes, exactly. So on the homework that I graded yesterday, I saw a handful that got sort of stuck at this point. So we have two terms. We just need to factor a GCF out. So we have 3x is our GCF. So 8 minus x is on the inside there. So we get x equals 0 and x equals 8. So we have our partition numbers for this, for n double prime, the second derivative here. But we should also remember.
But what are those two numbers called? Sorry.
These are the partition numbers of the second derivative.
Okay, and then we do critical, right?
So critical numbers are only for the first derivative.
Okay, thank you.
Mhm. Partition numbers can be found for any function, whatever we're focusing on at that time. But we have to remember what we're doing here. And at the very beginning of the problem, this said that x is going to be between 0 and 12. So we're either spending $0 on advertising, and this is saying we could go up to $12,000 since this is in thousands. So when we make a sign chart to determine concavity, we don't need to do negative infinity to infinity because we only care about 0 to 12. And 8 is one of our partitions. So the 0 is there, but it was an endpoint anyway, so it's not really doing that much. So since we're looking for concavity, whoops, that should be an n. We need to find, make a sign chart for the second derivative. So we could just choose any test points in between these numbers.
5 and 10.
5 and 10. Okay. And we would put those into n double prime. And I have a calculator on this computer. So we have 24 times 5 minus 3 times 5 squared, which is 45. So we have a positive number for that one. We know that second derivative is 0 at 8. And then we would just do the same thing for 10. And that one's a negative.
That's weird how it switches, because in my mind, I think if you do it by 5, then 10 should just be double of what the first answer was. It's weird.
Yeah.
I know that's not how it works, but I was like, I wonder if that's going to equal, and it didn't.
Nope. And that's why order of operations is important. Because since we're
Yes.
squaring it, the doubling doesn't happen. Okay, so now we know that this n double prime is positive from 0 to 8 and negative from 8 to 12. So that's telling us that our graph is concave up 0 to 8 and concave down 8 to 12. And so let's just look at what that question was again. So when is the rate of change of sales increasing and when is it decreasing? So to answer the question that's being asked, we should answer it in the same language. So the rate of change is increasing. And 0, 8, so that interval. Or we could also write it in interval, or excuse me, in algebraic notation. Either of those would be fine. And the rate of change is decreasing. On 812. There we go. So this problem was not actually new stuff. We have been finding concavity since last week, but it's just the wording is different. So we have to kind of figure out what is being asked here. So let's look at part B. So what is the point of diminishing returns and the maximum rate of change of sales? So let's focus on the point of diminishing returns for a moment. And I'm just going to scroll up to the definition just to remind us. So the dollar amount at which, and this is a little fuzzy, I'm going to talk about that in a second, in which the rate of change of sales goes from increasing to decreasing is the point of diminishing returns. So we've actually already done all of the work we need to have the point of diminishing returns for this problem, because it is just the x value of that inflection point. So on this problem, what is the point of diminishing returns?
8.
8, exactly. And so this is a little tricky with the wording of the definition. It's the actual x value in the function. So even though let me think about this before I. Yeah, so even though it would actually be $8,000 that we're spending on advertising, since that function it says X is in thousands of dollars, the actual point of the diminishing returns is just the X value from the function. So it is 8. Oops. Okay, come on, pen. So the other question for part B what is the maximum rate of change of sales? So let's think about what this graph would look like roughly. So we're going from 0 to 12 on our x, and we don't really need to know what the actual y's are. The important thing to know is that our graph is concave up until it gets to 8, and then it changes to concave down after that. This is not a very beautiful graph. So the maximum rate of change of sales is going to be the maximum slope. Since this is our sales graph and the rate of change is the slope, this will be the maximum slope, or in other words, where the slope is the steepest.
Since we're only going to 12 and it's going up to 12, is that where it stops? Is that right?
Yes, so it stops at 12 since the problem said 0 to 12.
Okay.
So where is this graph going to be the steepest if we look at all the little tiny tangent lines that tell us the slope along this graph? Where does it get the steepest? What x value?
It looks like
8.
8, yes. Heard a couple 8s. And that is always going to be true. Where if it's changing concavity there, it's getting super, super steep. So this rate of change of sales is increasing and increasing and increasing, and then it starts to decrease. So its maximum rate of change is where it gets the steepest after increasing a bunch, and then it'll slow down.
Is it typically always the same as the point of diminishing returns?
Yes.
Okay.
It is. But that's just telling us where we achieve the maximum rate of change. It's not telling us what the actual maximum rate of change is. So the maximum rate of change occurs when x equals 8 at the point of diminishing returns. We're going to plug that into something to find the actual maximum rate of change of sales. So far, I'm going to scroll up for a little second. We started with this n that we were given, which is the sales function. And in part A, we started with n, and then we found the first derivative, and then we found the second derivative. Of those three, which of them tells us the rate of change of sales?
The first derivative?
Yes, exactly. First derivative. Anytime we hear rate of change of our function, which is sales in this case, the first derivative is what we're looking at. So our first derivative is 12x squared minus x cubed. So the first derivative always tells us the rate of change of sales, or rate of change of whatever our function was. So if we know the maximum rate of change occurs when x equals 8.
Plug 8 into that.
Exactly. We'll just plug 8 right in there.
That last one's a cube.
Oh, thank you. Okay, so we have 12, 8 squared minus 8. 256. What are our units on that 256?
Would that be dollars?
Dollars will be part of it.
Rate,
Or whatever.
Ooh. What was that?
Per something. I don't remember what the question was about.
There is a per. Anytime we have a rate of change, it's always going to be something per something. So our y was n, which n of x, and the units there were TVs. So we were selling some number of TVs. X was thousands of dollars. So a rate of change is always going to be y per x.
So it'll be $256 per TV.
Other way around.
Okay.
256 TVs
Unit.
per $8,000 of advertising.
Just per 1,000. Because so it all our units of a rate of change are always the units of our y divided by our units of x. So this means that sales are increasing by $256. Sales are increasing by 256 TVs for every $1,000 spent on advertising at that moment.
So if you spend $1,000, you're going to sell 256 TVs.
256 more TVs than you were before.
Okay, so it's like past the break-even point. Or no?
We don't know what the we don't have a break-even point here because we don't have anything to compare it to.
Okay.
So we're just looking at how sales are increasing as we spend money. So as we go along this function, we're spending more and more thousands of dollars and sales are going up and up and up. And we could find the rate of change anywhere here. But once we get to 8, that's where the rate of change is the highest. So at that moment, for every $1,000 we're spending, we're adding 256 TV sales. And as we add more money in advertising, sales are still increasing, but the slope is getting smaller.
So past that point, your advertising dollars still are increasing sales. They're just not as effective as that point.
Right, exactly. So if
Okay.
we,
Let me just see if I understand. So once we hit $8,000 in sales, that's when it starts increasing the 256 for the 256 TVs. It goes up $1,000 after that. So like it'll go to 9,000, 10,000, 11,000, 12,000, or am I not understanding that right?
so for most of the functions we've talked about in this class, the dollars have been the y value, but we are switching that. So the thousands of dollars are what we are in control of. We can spend however much money we want to on advertising. And the sales are what are going to follow from that, the change in sales.
Okay. Sorry, I'm trying to switch my brain from programming.
Yes. And so no matter how much we're spending on advertising, the sales are increasing. So this is a fully increasing function on 0 to 12. It's just that we're selling more TVs for the money we're spending on advertising at when we're spending $8,000. Just for fun, this is not a part of the problem, but just for the sake of seeing what's going on here. If we checked like $4,000 and $10,000 just to see what's going on, we could check the rate of change of sales for spending $4,000. And the rate of change of sales for spending $10,000. Each of these should be smaller than 256, so let's make sure that that's true.
So 10 is 200.
Okay, and I just did 4, so 4 is 128. You said 200?
Yes.
Okay.
So $8,000 is when your advertising dollars are the most effective.
Exactly.
Above or below that would be still increasing sales, just not as effective as $8,000.
Yes, exactly. That's exactly right. So if we're spending $4,000 on advertising, our sales are still increasing by 128 TVs per $1,000. And if we're spending $10,000, our sales are still increasing by 200 TVs per $1,000. But those are just not as fast increasing as that $8,000. So $8,000 is our fastest rate of change of sales.
Thank you. That helps.
Okay. So that's actually the end of section 4.2. This is an application of that inflection point. So if we didn't have a context here at all, that would just be a regular old inflection point. But now we have some context to apply to it. So that's our point of diminishing returns. This next little section is going to feel a little bit out of place, probably, but it is an important, super important little calculus thing. Not little thing.
I was going to say there's nothing little about this chapter.
So this is going back to limits. And the reason we're talking about limits here is if we're graphing pretty complicated functions, we need to be able to find limits at certain points to see what their graphs are going to do. We're sticking with, we're not going to get any more complex than we did on Tuesday. But L'Hopital's rule, which is what 4.3 is about, is an important concept about limits. So we mentioned before, way back in chapter 2, indeterminate things. And so there are a couple indeterminate forms, and one of them is 0 over 0. And we actually saw this in chapter 2. If we plug something in and we get 0 over 0, we can't make any conclusions about that. It's indeterminate, which means we don't know what it is. So, for example, here is our first problem. Limit x as x goes to 0 of e to the x minus 1 over 4x. So our first thing we should always try when we're trying to find a limit is to just plug in the number that x is going toward and see if it works. And so if we do that, if we plug in 0, we'll have e to the 0 minus 1 over 4 times 0.
Undefined.
Not undefined,
Well, DNE.
not quite. So 4 times 0 on the denominator is 0. What is e to the 0 power?
0. Oh no, it's 1.
1, yes.
That's right. Okay.
Anything to the 0 is always 1. So this is not just a 0 in the denominator. This is a 0 in the numerator and denominator. So this is not undefined. This is indeterminate.
Okay, so if it was like 1 to 0, then it would have been 1 over 0, and then it would have been undefined.
Right, exactly. So if we have a not 0 number on the top and a 0 on the bottom, then it is undefined. But if we have 0 over 0, this is indeterminate. So all that means is that we cannot make any conclusions at this point. We have to do some more work to figure it out. And I didn't spell indeterminate correctly. Back in chapter 2, we saw this happen when there was a factor that could cancel on the top and bottom in the situation of a whole, but we were able to cancel those factors and deal with it in that way. This way, there's nothing to cancel. We have an e to the x minus 1 on top, 4x on the bottom. So we need some more methods. And so that is where L'Hopital's rule comes in. So the important part, well, yeah, it's all important.
You're starting to feel like my mom with all these rules. I think that L'Hopital's rule looks more intimidating than it is. Yes.
So, so C is just some number. So C is the number that X is going towards. And we're saying that the limit of the top, F, is 0, and the limit of the bottom is 0. So that means we have this indeterminate form where we try to plug in 0 on the top and 0 on the bottom, but we get 0 over 0, or C on the top and C on the bottom, we get 0 over 0. Then the limit of that whole thing is actually equal to the limit of the same thing, except we're just doing the derivative of the top and bottom. So all this is saying is that if we end up with a 0 over 0, take the derivative of the top, take the derivative of the bottom, and try it again and see what we get. So let's go back to that same problem. So L'Hopital's rule is telling us that this limit, so this is the exact same problem as above. We already know that this is a 0 over 0 situation. That limit is the same as if we take the limit of the derivative of the top over the derivative of the bottom.
So EX over 4.
Yes, exactly. So derivative of the top is just e to the x, since that 1 will go away. And the derivative of the bottom is just 4. So this is not a quotient rule situation. We're not taking the derivative of the whole quotient. We're just doing the top and bottom totally separately. And now, if we try that same thing and try to plug in 0 into our quotient, we have e to the 0 over 4.
1/4.
1/4, exactly. So this step was the L'Hopital step. We just took the derivative of the top and derivative of the bottom. And then we can plug in that number that x is going towards, and we got something. So the limit of this function as x goes to 0 is 1/4. So this is why this is called indeterminate, because we get this scary looking thing 0 over 0, which people want to say is undefined, but it's not. We just don't know what it is yet. And so we can do L'Hopital's rule to find out what it actually was. So neat.
How do people come up with these things?
Lots and lots of work and trials.
I wonder how long it took them to figure that out. Do you know?
I actually don't know. No. Can look that up. So let's try it again. So I want to highlight before we go farther. This only works if this is a 0 over 0. There's actually one more that it works for, which we'll see. But if we can get the limit from plugging in C, L'Hopital doesn't work after that. So we always need to check to make sure that we do have an indeterminate form. So let's try and just plug it in first. So if we plug in 1 here, we get 1 minus 1 over the natural log of 1. 1 minus 1 is 0, of course. What is the natural log of 1?
0.
0, exactly. Log of any base of 1 is always 0. So since this is indeterminate, we need L'Hopital.
And then that would be 1.
Let's see. So to L'Hopital it, we will take the derivative of the top, which is 1. X derivative of x minus 1 is 1. What is the derivative of ln x?
1 over x.
1 over x, yes. And so here we should do a little bit of simplifying with this expression. Oops. Which I'll just do here. 1 over x is the same as 1 times x over 1, which is just x. So that's just dividing fractions. And so if we plug in 1 to x, we do get 1. So some of these will end up with something that can simplify, and if we can simplify, we should, because it might turn out that we have something that we can work with after simplifying. So there's one more indeterminate form. There's actually some other indeterminate forms also that we won't get to in this class, but there's one more that we're going to work with, which is the situation that we have infinity over infinity. So our next indeterminate form is infinity over infinity. And L'Hopital works for this too. And L'Hopital should have a little hat. So infinity, you might have heard of different kinds of infinities. We don't know what infinity over infinity is necessarily. It could be one of the top is growing way faster than the bottom. It could be the bottom is growing way faster than the top. We don't know what's going on when we have an infinity over infinity. So we need a little help to help us figure out that limit. And L'Hopital is the right tool. So this is something that we were actually finding the limit of in chapter 2. And we didn't use L'Hopital at that time, but we can. So here, x doesn't necessarily, or excuse me, infinity doesn't necessarily like plug in for x, but if we think of it that way, this will be a bunch of infinity stuff on top because x is going towards infinity. And the bottom is also going to be infinity. Since we have x's on the top and x on the bottom, both of those are going to go towards infinity. So we need to use L'Hopital to help us with that. So we do exactly the same thing. Even though it's a different indeterminate form, L'Hopital's rule works exactly as it did before. So we'll do the derivative of the top. So 9x squared plus 2. And the derivative of the bottom, 8x. So if we think about x going towards infinity again, there's still an x on top. That x squared is still going towards infinity. And the bottom, 8x, is also going towards infinity. So this is still infinity over infinity. Because they both have an x that's going towards infinity. So since it's still indeterminate, we can do L'Hopital again. So the top here, if we do the derivative again, we get 18x. And on the bottom, we have just 8. This is no longer indeterminate because the bottom is just an 8. That's not an infinity. It's not going to go towards infinity because x will not change that 8 at all. There's no x to change it. So we L'Hopital until we're out of the indeterminate forms. And then we just have to do a little bit of thinking. If x is getting bigger to infinity, what is 18x over 8 going to do?
Yeah, infinity over 8.
Yes, but 8 is not going to change, so it is actually just infinity.
Ah, okay.
Because if we're at infinity, a little 8 on the bottom isn't going to affect anything.
What would affect it?
Only another infinity.
Okay.
But it depends on how big it is. So on this case, so if we think back to chapter 2, this was like a horizontal asymptote, or not horizontal. This is an asymptote situation where we would compare the degree on top and bottom. Since the degree on top is bigger, this would be a slant asymptote. And so it's actually going off to infinity, or negative infinity would also be possible, but this case we had positive over positive. So it's because the top is getting bigger faster than the bottom. So it goes off to infinity.
So what happens as it approaches negative infinity, as x approaches negative infinity?
Good question. So if we can start with that last our last L'Hopital, because it would have been some sort of infinity over infinity all the way up till there. I'm gonna write it in a way that's not fully proper, but if we plugged in a negative infinity, which is not really a thing we can do, but we can imagine that that's what's happening. Now all of these x values that are getting smaller and smaller and smaller are going towards the negative infinity side. And so it's still 18 times that negative infinity, or times whatever really small numbers are going down, over 8. So this would end up being negative infinity, because we know that these values are all going to be negative. If this happened to be a negative 18 there, those two would cancel each other out and it would end up being a positive infinity.
Can you draw what the lines would look like on a graph for those two? Just so we can see.
Yeah, so this would be, this rational function would have a slant asymptote that would be doing something like this. And it would probably, and it has a vertical asymptote here. So this graph would look something like this. So as x is going towards infinity, y is also going towards infinity. Not quite as fast, but it's still going up. And as x goes towards negative infinity, y is also going towards negative infinity.
So the top one is the top infinity and the bottom one is the bottom infinity?
Yes, because here x is going towards positive infinity, and here x is going towards negative infinity. In
Gotcha.
this direction. Okay, so let's do a couple, one or two more. So this is one that first one, sorry to go back suddenly. This is one that we could have figured out using algebra knowledge. This is the kind of thing we were doing in chapter 2. But L'Hopital still can apply. The second one, we need L'Hopital. We don't have any previous algebra knowledge that will let us do this second one. So if we just imagine this one, again, what's happening, x squared. I'm just going to plug in infinity just to show what's happening. Infinity squared is definitely going off to infinity. E being raised to some infinity is going to infinity. So both the top and bottom are getting really, really big. So we need L'Hopital.
It'll be 2 over e to the x.
2x over e to the
Oh.
x. Oh, and if you're going one more step, then yes. So we need to L'Hopital as many times as necessary. So that 2x over e to the x is still indeterminate. This is still infinity over infinity. So on this next one, we end up with 2 over e to the x.
Be 2 to infinity. Over infinity.
We can think of it as 2 over infinity, but that actually is a value. What happens to a fraction if the denominator just keeps getting bigger and bigger and bigger, but the numerator doesn't change?
Keeps getting smaller and smaller and smaller.
Yes. Keeps getting smaller and smaller and smaller. So what would its limit be? What would it be getting closer and closer and closer to?
Negative infinity.
Not quite. Because this 2 over infinity is never going to be a negative number. We have a positive 2, and that infinity is going in the positive direction.
So then 0.
0, exactly.
Oh.
And this is actually a similar concept as in chapter 2. Again, when we have a rational function with the degree on the bottom is bigger, it always goes to 0. And that's a similar concept here. That bottom is getting super big and the top is not changing at all. So if the bottom grows faster than the top, or the top isn't growing at all, our limit is 0.
So is it safe to say that anytime there's an infinity in the denominator, it's always 0?
Yes, as long as there's not an infinity in the numerator also, yes. If it's just a number over infinity, it's 0. And that's for positive or negative. Either way, it's going to go towards 0. Okay, let's do one more L'Hopital.
It'll be infinity over infinity. Oh, wait.
I'm second guessing this example right now. Just a sec, let's check. Let's see if I made a bad example. So e to the negative x is actually the same as 1 over e to the x.
Oh.
And ln of x is just itself. So this is actually not a good L'Hopital problem because it's not really indeterminate. E1 over e to the x would just have a limit of 0 because we have that same kind of situation here. If the denominator is getting super big and the top is not changing, that's just 0.
And then over infinity.
Exactly, over infinity. Natural log of x as x goes to infinity is going to be infinity.
Which then will be infinity. Oh, no, 0.
0, yeah. So that was a silly question. We didn't actually need L'Hopital there, but that's a good exercise in thinking about infinities. So this works for any time we have a quotient of two functions, so some function over another, and if we try to plug in that number or plug in the sake of infinity, if it goes to 0 over 0 or infinity over infinity, we have to use L'Hopital to help us. So there's usually not a whole lot of work that goes into these, but then there's a little bit of like thinking at the end, like what's going on here if we have 2 over infinity? Any questions about L'Hopital? Okay. So 4.5, we're just going to sort of breeze through, and there's one important test that we're going to talk about. So 4.5 is about absolute maxima and minima. So we've been talking about local maximums and local minimums, which is what our focus is going to continue to be. So you don't need to even have these written down because we're not really going to work with them, but just as a note, an absolute maximum is the very biggest maximum for F. So if we have a local maximum, that's just sort of a little hump, but there could be higher values elsewhere. And so the absolute maximum is the absolute highest. Absolute minimum is the absolute lowest. So we can have lots of local maximum and minima, but there's only one absolute maximum and one absolute minimum.
Is that kind of the same as global maximum?
Yes, yeah, it's
Okay.
the same. Yeah, just a different word for the same thing. And there is an important, this is a picture in the book. So this is in the book. You also don't have to have this necessarily, but it's a fact that if we have a closed interval, so we have like set endpoints instead of like ends that go off. If we have a set endpoints on a closed interval, there will always be some maximum, absolute maximum, and always be some absolute minimum. But it depends on where we're cutting off that interval. So on this first graph, our absolute max and min are on these ends. But if we make our interval smaller, then those, oops, that's the wrong place, then the absolute maximum and the absolute minimum change. So we're always looking for the very highest point and the lowest point on that interval. And the one theorem, which is important, but we're not really going to use in this class, is the extreme value theorem, which says that if a function is continuous, so no holes or asymptotes or anything like that, on a closed interval AB, it always has an absolute maximum and absolute minimum on that interval. If we don't have a closed interval, it's not necessarily the case. For example, if our function goes on forever in each direction, there is actually no absolute max or min here, because it's going off to infinity in each direction, so it never actually reaches an endpoint. But if we take that same graph and cut it off onto a closed interval, which is what the AB part is, now it does have an absolute max and absolute min. Our maximums and minimums that we're going to be working with in the next section will be local maximums and minimums. So we don't need to worry about this now, but this is a fact. If we cut off an interval and we're just looking at that interval, it will have some maximum and some minimum. The rule or test that I want to highlight from this section is unrelated to the, well, it is related, but is actually about local extrema, and that's the second derivative test for local extrema. And this is on the book on page 297 as well. This is actually optional in this class because we know how to find local extrema. We have ways to do that, but this is like another sort of streamlined way to find them. And so in section 4.6, we will be finding maximums and minimums, and this is an alternate way to do that. So the second derivative test for local extrema tells us if C, or if f prime of C equals 0, that means that C is a critical number. We know critical numbers, or any place where the first derivative is 0 is a critical number as long as it's in the domain. And if f double prime of C is positive. If the second derivative is positive at some point, what does that tell us about the concavity of the function at that point?
It's increasing.
What is increasing?
The
It's concave up.
yeah.
Concave up, yes, which means that the rate of change is increasing. But the function itself is concave up. So if we have a critical number, which is going to be a place where the tangent is 0, or excuse me, if we have the first derivative equals 0, so the tangent is 0, and our graph is concave up at that point, then there has to be a local minimum there. So if f prime of C is 0 and f double prime of C is greater than 0, then f of C is a local minimum. So the first derivative being 0 means we have a flat tangent there. But if it's definitely concave up there, that means the graph is turning at that point, and it must be a local minimum.
If the left side of that graph was also increasing, wouldn't there still be a critical number at 0?
There would be a critical number, but so if we had something like this,
Yeah.
the f prime would be 0 here. So yes, oops, not 0. But what is f double prime there?
To the right is concave up, to the left is concave down.
Exactly. So actually at that point specifically, it would still be 0. So we can't say, or so this is specifically at that point C, the function is concave up. At this point, the function is not concave up or down at that specific point. So this one does not fit the conditions of that first bullet.
So it's like a transverse plane. Is that kind of?
I don't.
know if that's the right terminology, but
This is an inflection point.
okay. So it's like the flat point. Okay.
So why is f double prime greater than 0 at that point?
This one?
Yeah.
Because the graph is concave up at that point. It's concave up all the way through there.
Okay.
It could actually be 0 there, which is not a situation we're looking at here. But if the f double prime is greater than 0, then it's definitely a local minimum. This statement does not reverse. We cannot say if it's local minimum, then these two things are true. That's not always the case. But if we have f prime equals 0 and f double prime is greater than 0, then there's definitely a local minimum there. So if we look at this other statement, so again, we have a critical number. So f prime of c is 0, so this is critical again. And this time f double prime is less than 0. So we know that at this point C, there is a horizontal tangent and it's concave down at that point. Then we definitely have a local maximum. This test breaks down if the second derivative is 0. So if we have f prime of c is 0, so still a critical number, but the second derivative is also 0, we can't say anything. So this test doesn't help us at all if the second derivative is 0. Lots of different things can have a second derivative of 0. It doesn't mean that there's not a local maximum or minimum there, but it doesn't mean that there is either. So you, when you are finding local maximum and minimum, you are welcome to use this, but you're also welcome to just stick with the sign charts that we were doing in 4.1. So this is an option, but it's not required. But I want to use it in our next problems that we're going to do just to see how it works. Okay. So we have, I'm going to put up a poll in just a second. So this is just a general revenue graph. We don't have an equation or anything right now. And this is, so revenue per units that we are selling. So sort of our standard revenue function. We're selling X units and we make our revenue. So I'm going to launch a poll. We have 4 points on this graph. And the question is, what point on the graph represents the maximum revenue? Ten more seconds. Okay, I am ending the poll now. Okay, wonderful. So that went well. C is where the maximum revenue happens. So the maximum revenue is actually here. It's the highest point that our revenue curve reaches, and it's achieved when we sell this many units. So we're going to apply the same idea of maximum and minimum to revenue, profit, and maybe other things. So optimization is the title of section 4.6. Optimization is a huge field in math, or a really important part of math. We are working in 2 dimensions, x, y, for specific things, but we can expand optimization to any number of variables and lots of different pockets of calculus. And so anytime we're trying to optimize something, so that means like find the maximum revenue in this case, or find the most efficient way to send data to your Netflix streaming so that you get the best picture with the least bandwidth, or anything like that, that is all using these principles of optimization, which we've already learned, we just haven't called it this yet. So anytime we're trying to be efficient with anything, or find the maximum thing or the minimum thing or the most efficient thing or anything like that, we are looking at optimization. And so we know a few things about this curve if we're just looking at this function here. At that point, I don't have an x value for it, but the first derivative is 0, just like it has been for all of our local extrema. And we actually can't make an assumption about the second derivative, but this curve is concave down, so the second derivative is probably negative. So we're going to use our same principles of looking for maximums and minimums for finding maximum revenue, maximum profit, and some other things. So here is our first example of an optimization problem.
Is it 100?
I don't know. I don't have the answer in front of me.
Okay.
Let's find out. So I was just giving you time to read and write and start if you wanted to. So an office supply company sells X heavy duty paper shredders per year at P dollars per shredder. Price demand equation is this. So we want to know what price the company should charge to maximize revenue, to make the most revenue, and what is the maximum revenue. So in order to find maximum revenue, we first need our revenue function. What is our revenue function?
P times X.
P times X. So in this case, P is 300 minus X over 30. And so just like we did back in some chapter before, to get the revenue function, we're multiplying the price times the number of units that we are selling. So our revenue function is 300x minus x squared over 30. So we will always be first when we are trying to maximize something or minimize or whatever we're doing, we need to find the function for that thing. So if we want to find the conditions that will give us the maximum revenue, we need the revenue function first.
The derivative?
Yes, exactly. So we know that wherever the maximum revenue is happening, the derivative is 0, just like all of our other maximum and minimum. So we will take the derivative. So that 2 that comes down is going to cancel with the 30, so we have x over 15. And so we want to know where there is a maximum, which means we need to know where the derivative is 0.
I was way off.
That's okay. So when we solve for x, we will get 4,500. So technically, at this point, we know that the derivative is 0 when x is 4,500, but we don't actually know if there's a maximum or a minimum or just a little squiggle there. So we need to check to see what is happening at this critical point.
I'll plug in 45 to just Rx.
Not quite.
The derivative?
Not quite.
I'm gonna do the sign chart.
Yes, so we have 2 choices. So in from our 4.1 stuff, we would make a sign chart to see if it's increasing or decreasing on either of these sides to see if it's a maximum or minimum or neither. I want to use the second derivative test here just to show how it works, but you can use a sign chart still. So we need to know if this is a max, min, or a neither. So our first option make a sign chart of f prime, r prime in this case, excuse me. Option 2 is the second derivative test. So since you have lots of practice making sign charts, I want to use the second derivative test so we can see how it works. To use the second derivative test, we need to find the second derivative.
-1.
Not quite.
Over 15.
Yes, exactly. So technically the coefficient of x on r prime is -1 over 15. So we need that whole thing.
How come the 15 doesn't disappear because it's a coefficient? Because it's a product or a
Yeah.
quotient?
Right, exactly. So anything that's multiplied to x, which technically this would be 1 over 15 times x, or divided, like this divided by 15, doesn't go away. It's only things that are added or subtracted by themselves that go away. So here, normally, or if there were an x left over, we would plug in that 4,500 to see what's going on at r double prime at that point. But here, r double prime is always -1 over 15, which is negative. So
It's a
this
concave down.
Yes, exactly. So it's concave down. So the second derivative test says that r prime of 4,500 is 0. We know that from solving r prime for equal to 0. And r prime is negative anywhere, which means it's also negative at 40, sorry, r double prime. R double prime is negative everywhere because it's -1 over 15, which means it's also negative at 4,500. So there is a local maximum at 4,500, and that's r of 4,500. So these two, what's been happening a lot today? What's happening?
I like your backdrop.
Thank you. It's the Mandelbrot set. Okay, so we have these two conditions. If r prime is 0 and r double prime is negative, then we definitely have a local maximum. So the second derivative test has confirmed that this number we found earlier by setting the first derivative to 0 is in fact going to give us a local maximum. So this is something we could have done with a sign chart. So if we made a sign chart, we would have found that R prime was positive and then negative, and we could also see that that was a local maximum that way also. So either one of these you can do.
Real quick, Madeline,
Mhm.
if that R or the second derivative of with the 4,500, if that was say like -1, would we have a problem as far as the local maximum?
Nope.
Okay.
If it's negative, no matter what negative number it is, it'll be a local maximum.
Okay.
We would have a problem if it were 0. If it were 0, then the second derivative test wouldn't work and we would have to make a sign chart. So we haven't actually answered the questions that were asked though, so let's go up again. So the questions were, what price should the company charge to maximize revenue? And what is the maximum revenue? So we haven't answered either of those questions. We found X, which is how many paper shredders they need to sell. So if we know that X equals 4,500 is going to give us a maximum revenue, how can we figure out what price we should charge?
Plug 4,500 into the price equation.
Exactly. We have that price equation to start off with. Nope, that's not right. That was just an X. And so we can just plug in that 4,500. And we get 150. So this company should charge $150 per paper shredder if they're looking for the maximum revenue. The other question was, what is the maximum revenue? So how do we find that?
Plug P into the derivative.
Into the revenue function.
Revenue.
So our revenue function is a function of X.
So plug $4,500 or 4,500 units into the revenue function.
Yes, exactly. And I realized we could have done another way, which is maybe what you were suggesting, but let's start with this. So yeah, so we would plug in 4,500 because that is the number of paper shredders we found that will give the maximum revenue. Which is $675 million. Or the other way that we can always think of revenue as P times X, the price times X. So if we already found that price of 150, and we know that we're going to be selling for 4,500 paper shredders, we could also use those two numbers. Hopefully we get the same thing. Yes. So we found this situation where if we sell 4,500 paper shredders at $150 each, we will get that maximum revenue of $675,000. I think I said million before, and that's not right.
You did.
Thank you. Yeah, my brain is off on spring break. So these optimization problems are not going to be like new things. If you want to use the second derivative test, that's a new thing, but you don't have to. You can still use the sign chart. It's just applications of what we were doing in previous sections, finding maximums. And there could be a situation where we want to minimize something as well, minimize costs or something like that. Either way, we're finding those critical numbers, figuring out if we have a maximum and minimum, and then we can use that number we found to find all of the information we need. So that is all. I'll post just a little bit more to the homework that'll be due the Tuesday after spring break. I will also post either today or tomorrow some detailed information about test 3, which will be after spring break and will be a take-home test. So have a great couple weeks, and I'll see you next Tuesday.
Thank you, Madeline. Have a great day.
You too. Thank you.
Thanks. Bye-bye.
Thank you.
Welcome.
You have a great day, Madeline. Thank you.
You too.